My name is Yunting, and here there are 3 other colleagues who are contributing this project, including Liang Li and Xiang Lu and Professor Salvatore Tasso. And these results are based on 2 research projects, which are sponsored by GEA, EPRC, Innovative UK, and Manda Graphics, and also Brunel's IAE funding. And also there are some industrial contributors for these projects, including SWIP and also Innovidia company. So the main contents of my presentation are listed in this page. And firstly, I will give a brief introduction about the test rigs. 2 test rigs. One is CO2 power generation system. Another one is R2458 ORC system. And then I will give you some test results for these 2 test rigs, and for CO2 test rig and also R2458 test rig. And we give some test results at some limited operating conditions, and then we set up modeling for these 2 low temperature power generation system, so that we can enlarge the operating state and give more test results for the systems. And then I'll give you some conclusions. So these 2 low temperature power generation systems are installed above 1 CHP unit, which has 80 kilowatt power generation. And you can see here the CHP system. And these 2 ORC system, or low temperature power generation system, are heated by hot thermal oil, so which is heated by fuel gas and oil heat exchanger, where the CHP exhaust gas and the hot oil is circulated by the thermal oil pump to the ORC systems. So where oil rig here. So both test rig are installed here in the left top, that one. On the right side is the pictures of the test rig, that one. And if you are interested, I can show you after my presentation about the test rig. And the first one is the low temperature, we call it low temperature transcritical CO2 power generation system. And the system layout is shown here, that one. And we also saw some component pictures in this page. So the first one is the CO2 turbine here, you can see here. And another one is the air-cooled condenser here, that one. And the recuperator, the plate type recuperator, and also the receiver here. And liquid pump, CO2 liquid pump, and it's a bit oversized comparing to the power generation of the system, that one, and also the plate gas generator. So I just give you a brief description about the operation of the system. The high temperature and the high pressure CO2 flowing into the turbine to generate the power, and after that, the temperature and the pressure are both reduced. And then the CO2 will flow either going to the recuperator, which is controlled by the 2-way valves, or directly going to the air-cooled condenser to be condensed. And after that, the refrigerant will be changed to liquid state and will flow into the receiver, that one. And the circulate pump, liquid pump, will circulate the liquid CO2 and the pressure up the liquid, and the liquid refrigerant will go into the gas generator, which is heated by the hot thermal oil, and then flow into the turbine inlet and then generate the power. It is a cycle. So in this test rig that you can find out, we call it this is low temperature CO2 transcritical power cycle, because the high pressure side, the CO2 is in supercritical pressure, and the low pressure side, the CO2 is under the supercritical, is subcritical, so we call it transcritical power cycle. And since the hot oil temperature is about 200 degrees, so this is low temperature heat source. So we call this system is low temperature transcritical power cycle. So, and the next one is the R244A ORC test rig, this one. This system, the components is very similar to the CO2 test rig, but this system is working under a subvertical cycle, that one. So the high pressure side and the low pressure are all working under the critical point, that one. And in this system, the other difference is we utilize two expanders, that one, so that we can compare the performance by using different expanders. So one is the screw expanders, and one is the turbine. And we also utilize two evaporators. One is a plate evaporator, another one is the cell and the tube evaporator, so that we can compare the performance when the system utilizes different components, that one. So, and the working mechanism is similar, that one. The refrigerant going through the expander to generate power and then condensed inside the air-cooled condenser and circulated by the liquid pump and then evaporated by the evaporator, heated by the hot oil, that one. Yeah, the right side is the picture for the whole system. It's not that clear, but I think I can also just show you two pictures of the expander. One is this one. This is the screw expander, and this is the motor generator, actually. Yeah. So what I do, I just show you some test result for these two low temperature power generation system. The first one is for the CO2 system. So we designed the test matrix. So we just specify the range of the heat source parameters, including the temperature and the flow rate, and also heat sink temperature and the flow rate for the air side, and also the flow rate of CO2, mass flow rate, which is controlled by the liquid CO2 pump, that one. So for each test, we just change one parameter and to see the effect of that parameter on the performance of the system. So this test result just show you the parameter of the heat source thermal oil flow rate on the system performance here. So we change the thermal oil flow rate from 0.36 kilogram per second, increase to 0.463 kilogram per second. And we know the CO2 mass flow is controlled by CO2 liquid pump. So if we change the motor frequency of the CO2 liquid pump, you can see the CO2 mass flow rate change at different thermal oil mass flow rate. You can see when you increase the CO2 motor speed, the CO2 mass flow rate can increase, that one. But you can see the thermal oil flow rate doesn't change much about the CO2 mass flow rate. So this is what we can see from that. So you can see how can the motor frequency control to control the CO2 mass flow rate. And another result show you the still effect of the thermal oil mass flow rate on the pressure at the turbine inlet and outlet. You can see. So the top is the pressure of turbine inlet. You can see when you increase the motor frequency or increase the CO2 mass flow rate, the turbine inlet pressure will increase, that one. So when you increase the thermal oil mass flow rate, the turbine inlet pressure increase slightly, not that much. Similarly for the turbine outlet pressure, so when you increase the CO2 mass flow rate, the pressure increase slightly of the turbine outlet. So these two pressures are quite important, which determine the power generation from the turbine. So that's why we test the effect of the heat source parameter on these two parameters, that one. And again, you can see the oil mass flow rate doesn't affect much to the turbine's inlet and outlet pressure. This is what we found from at constant oil temperature. This we found from the test result. And another effect of the thermal oil mass flow rate is on the thermal turbine's inlet and outlet temperature. That one. You can see when you increase the thermal oil mass flow rate, the temperature of the turbine inlet and outlet are slightly decreased. That one. And comparing to the effect of the thermal oil mass flow rate on the pressure, so the effect on the temperature is a bit higher than the effect of the thermal oil mass flow rate on the pressure. You can see that one. So the oil temperature is no change. You can see this. This is another result of the effect of the thermal oil mass flow rate. That one. Yeah. Another thing is the heating capacity. So so we can use the different heat source parameter to control the heating capacity of the gas generator. So we can see the result from this page. So when you increase the mass flow rate, the heating capacity of the gas generator is slightly increased, that one. And on the other hand, so when you increase the thermal oil mass flow rate, the heating capacity of the gas generator is also increased a little bit, that one. You can see it from this type. So when all other parameters are kept constant. So this is the other test result. And regarding to the power generation, and from the system of the CO2, you can see here, we give two results. That one, yeah, the top one, you can see the power generation is about 1,000 kilowatts. This one, we don't consider about the mechanical and the electrical efficiency. That one, so you can have. So this result is only calculated out from the measurement of the CO2 mass flow rate and also the difference of the entropy at the turbine inlet outlet. So this is actually from the calculation of the measurement, that one. Yeah, without considering about the mechanical and electrical efficiency. But this result, you can see we can only generate about 400 kilowatts, which is quite low, that one. Yeah. Watts, sorry, 400 watts, yeah, which is quite low, that one. I think this is because this is from the measurement from our power meter. I think that this something, I think, so because of if you see the right side diagram, you see that one. If the isentropy efficiency for that turbine is about 40%, that one. So if this one is reasonable, you can see the overall efficiency is quite low because of the mechanical and the electrical efficiency. So this might be, I think, need to be improved in the future for this particular scales of system, that one. And you can also see the effect of the heat source mass flow rate on this efficiency and also the power generation, so on. So we just gave this CO2, this test result. We also have some other results. Because of time, I think I can only present this. And what I want to say, I think, because of the CO2 is working in under the transcritical cycle, and the high pressure side is very high, and the test was quite difficult to carry out because of when you do the test, you can have some risk of leakage. So we have some limited test results for the CO2 system. And I also, at similar operating conditions and similar design the condition for the test. So I also present some results for the R24A ORC system, that one. And this time we will see the effect of thermal oil temperature on the expander's inlet and outlet pressure, and also the power generation from the turbine, that one, at different thermal oil temperature. So the first one you can see when you increase thermal oil temperature, that one, the turbine inlet pressure will increase, and the turbine outlet pressure is slightly, not that much, slightly increased as well. And if you calculate out the pressure ratio, when you increase the oil temperature, the pressure ratio of the turbine will increase as well, that one. So when you keep constant for the other parameters. And if you look at the power generation, so when you increase the heat source temperature, thermal oil temperature, the power generation will increase, that one. And the efficiency will increase as well, that one. And the blue color one, you see, this one is we call it the system thermal efficiency. This blue color, this, can't see there. So this one, so the top one is the power generation from expander, and the red color is the power consumption of the pump, that one. And you have two efficiencies, the blue color, purple color, and also that one, and the light yellow color, that one. See, that one is similar to the CO2 system, the higher efficiency, and which is without considering about the mechanical and the electrical efficiency. So the efficiency is higher than the system's net efficiency. So this is the result, and another result is for the turbine's efficiency. You can see this one, and this the blue one. You can see this isentropic efficiency, and the red one is the overall efficiency. So again, I think for this system, the mechanical efficiency and electrical efficiency and need to be improved, that one, so that it can match to can give a higher overall efficiency. So as I mentioned, I think because of the limitation of the test rig, the components, and also the controls, so if you wanted to have quite a large scale results, you can't purely rely on the test. You have to, I think the better way is to set up modeling for the system so that you can simulate out the result performance or the system performance enlarged in that operating state. Okay, I'll speed up. So, and then we set up the simulation, the modeling for these two systems. So this is the CO2 system, and we developed the modeling for each component, and then we assemble this component model under the transit environment and connect them together and to run and to give the result for the system. And I think because of time, I just present one component model, which is the plate heat exchangers. No matter it is evaporator or recuperator or gas generator. If it is evaporator, we divide the whole heat exchanger into three parts. That one. If it is a gas generator or recuperator, we can assume the whole system is just one part. And for each part, we set up the energy balance or pressure drop, and also the mass balance for each part, and then we set up the modeling. And I'll just give you some results. I don't know why it's like that. And so this is the simulation conditions, that one. So again, so we specify the range of the heat source parameters and the heat sink parameters, and also the turbine's pressure, and also the power generation. We want to see the effect of each parameter on the system performance. And I'll quickly go through that one. So you can see here, this one, if you change the heat sink temperature and if you change the pressure, you can see the CO2 mass flow rate. So this time, what we want to do, the target is we want this system to generate 5 kilowatt power generation power. So no matter what the condition is, so at different opening ambient temperature and different pressure and different heat source temperature, you can see what the CO2 mass flow rate is required, so that you can find a method to control the CO2 liquid pump, that one. And that diagram, you can see when you change the heat source mass flow rate, the CO2 mass flow rate doesn't change much. So again, we can demonstrate the effect of the heat source mass flow rate not that much compared to the heat source temperature. That one, yeah. Okay, and the summary conclusion, yeah, that will be all the time, and how, yeah. So the test rig of TCO2 and R244A ORC were developed, and the measurements were carried out at various heat source and heat sink temperature parameters. And the heat out temperature has a greater effect on system performance than the heat out flow rate. This is what we can find out from tests and simulation. And the system overall efficiency is affected significantly by the system design, heat losses, and the pressure drop and the expander performance. And the system model have been developed and used to simulate performance over a wide range of operating conditions and capacities. And the simulation can contribute significantly to understanding of system behavior, design, optimization, and controls. Okay, thank you. Yeah.